Welcome to Tomorrow Unveiled, where we take the vast, overwhelming ocean of information and distill it down to the most critical insights you need to know. And the pace of development in the aerospace sector this week isn't just fast, it's honestly dizzying. We're going to cut through all of that noise to deliver the three crucial insights you need to know about what really feels like a genuine pivot point in space history.
It really does. I mean, it's the first quarter of 2026, and every single source our dedicated research team has analyzed confirms that the velocity right now is just unprecedented.
Yeah.
This is not the space race of the 1960s, flags and footprints. This is a strategic infrastructure race. The consensus is crystal clear. We're witnessing a massive shift from experimental missions to establishing permanent, resilient capabilities.
So we're moving from discovery to deployment.
Aggressive, permanent deployment, both near the moon and right here in orbit.
Absolutely. So for our analysis on Tomorrow Unveiled, we've synthesized intelligence across, well, multiple domains. Our mission is to focus on three major themes that, when you put them together, really define this moment. First, the imminent countdown and staging of the American lunar campaign, Artemis II.
A huge one.
Second, the really shocking implications of a medical crisis that forced an early crew return from low Earth orbit. And third, these radical materials, science, and propulsion breakthroughs that are enabling us to build spacecraft that could literally last for centuries.
It's a week where you have this collision of immediate operational risk on one hand and decades-long strategic planning on the other. It's an incredibly important moment to really separate the signal from the noise.
Let's start with the loudest signal this week, which is, the physical movement of America's ambition. The clock is ticking on that Artemis II launch window, and the big news is the readiness for the massive rocket stacking to finally begin its trip to the pad. The atmosphere at Kennedy Space Center this week must just be electric. The major step that was just announced is the rollout of the fully integrated Space Launch System, the SLS rocket, with the Orion spacecraft perched right on top. This movement is such a tangible sign that the pause on human lunar exploration that stretched for over half a century is finally ending.
It's way more than just a tangible sign, though. It's the ultimate staging event right before the crucial final tests. Our research team tracked the target window for that multi-hour journey to launch pad 39B.
And when are they aiming for?
No earlier than 7 a.m. Eastern this Saturday, January 17th. Once that stack starts moving, the countdown to a crewed lunar flight becomes very, very real.
It's just so difficult to grasp the magnitude of this thing. 322 feet. Can you even put that in context? It's the size of a skyscraper that's been designed to withstand the most violent forces imaginable.
For sheer scale is staggering. To help you visualize it, the Statue of Liberty from the ground all the way to the tip of her torch is about 305 feet.
Right.
The SLS stack at 322 feet is significantly taller. And while, some of the initial weight reports can be a bit misleading, the unfueled, fully integrated stack, that's the core stage, the solid rocket boosters, and Orion is roughly 3.5 million pounds at rollout.
3.5 million pounds.
It's an astronomical amount of complex hardware that has to move as one single, perfectly balanced unit. It's incredible.
And the part that's often overlooked is the engineering spectacle that actually moves this behemoth, this slow trek. The journey is only 4 miles, but it takes hours.
Up to 12 hours. For a 4-mile journey from the Vehicle Assembly Building, the VAB, to launch pad 39B. And that's because the vehicle carrying it, the Crawler Transporter 2, moves at this glacial maximum speed of just 0.82 to 1 mile per hour.
1 mile per hour.
It's a remarkable piece of logistics infrastructure all by itself.
What's fascinating to me here is the dual nature of the technology being deployed. We're using the most advanced high-thrust chemical rockets ever developed, but they're being carried to the pad by infrastructure that was originally built for the Apollo program's Saturn V rockets.
And that's precisely the critical implication we need to draw from this. It really highlights the challenges of these massive infrastructure projects that rely on decades-old high-maintenance logistics.
It's a bottleneck.
It is a bottleneck. That Crawler Transporter is a testament to long-term engineering vision, for sure. But any delay in its operation immediately impacts the entire schedule for the whole lunar campaign. It just shows us that even with these revolutionary rockets, our ability to launch is still constrained by legacy ground operations.
So shifting to the mission itself, Artemis II is the first crewed Artemis mission. It's the first human flight around the moon in over 50 years. The crew of 4 Reed Wiseman, Victor Glover, Christina Koch, and the Canadian astronaut Jeremy Hansen, they're slated for a 10-day test flight, but this test is absolutely crucial.
Oh, the stakes are enormous. And not just for the 4 astronauts, but for the entire future of deep space exploration. The goal of Artemis II is the absolute validation of the Orion spacecraft's ability to function in that extreme cislunar environment.
So it's a systems check.
It's a systems check, a safety check, and a performance check all rolled into one mission.
But before the crew even gets on board, there's one make-or-break test that's still looming after the rollout, the wet dress rehearsal, or WDR. Our research suggested this is the critical gate they absolutely have to pass.
It is the single most critical near-term test. They've slated a full fueling test for February 2nd. The WDR is where they load all the cryogenic propellants, liquid hydrogen and liquid oxygen, into the core stage. They run the countdown sequence almost at T0, and then they safely drain the vehicle.
Okay, so what are they looking for?
They need to prove, without a doubt, that the core stage can handle the massive temperature and pressure changes that are just inherent to cryogenic fueling.
And why is this specific WDR under such intense scrutiny this time around?
Well, it's because of the technical issues they encountered during the Artemis I WDRs, which necessitated some significant redesigns and fixes. The main concern centers on fuel leak management,
Right.
particularly with the complex seals and plumbing needed for liquid hydrogen, which is just notoriously difficult to contain because of its extremely low temperature.
So they need to prove the fixes worked.
If those fixes, which they've implemented over the last year, are not completely successful, if this WDR reveals unacceptable leak rates or other structural stress, it could immediately push the entire launch timeline back significantly.
And if that test on February 2nd goes perfectly, the initial launch window is just 4 days later. That seems incredibly tight.
It is. The current, very aggressive launch window is February 6th to the 10th. Now, missing that window isn't catastrophic, but it forces NASA to rely on subsequent monthly opportunities.
And those are dictated by physics, I assume.
Exactly, by orbital mechanics, lunar alignment, and the sunlight angles they need for both launch and the return splashdown. While NASA's launch director, Charlie Blackwell Thompson, confirmed they do have launch windows available every month, the immense pressure, both political and operational, is to secure that early February slot.
Delays mean more money.
Delays mean increased costs and, maybe more importantly, potentially losing momentum to international competitors.
Let's focus on the Orion spacecraft itself for a moment, because this isn't the same Orion that flew on Artemis I. What makes this specific piece of hardware the key to the success of this test flight?
That hardware distinction is absolutely vital. The Orion capsule they used on Artemis VI was essentially a demonstration vehicle, a shell.
Right, a test article.
The Orion on Artemis II is the first to include all the active, validated life support systems necessary to sustain a human crew for 10 days beyond Earth's protective environment. This means carbon dioxide scrubbers, oxygen replenishment systems, radiation shielding protocols, redundant emergency systems, the works.
So Artemis II is really about validating the whole life support infrastructure in deep space.
It's the final human-rated stress test before Artemis III, which is the mission that will finally put humans back on the lunar surface.
This whole program, though, it relies on so much more than just engineering. It relies on consensus, on international law. The Artemis program isn't just a technical endeavor, it's also trying to set the gold standard for international exploration governance through the Artemis Accords.
The diplomatic context is arguably as important as the propulsion system. Our research team highlighted Portugal's recent signing, which makes it the 60th nation to formally join the Accords.
60 nations! That's a massive coalition.
It's a huge diplomatic victory for the American-led initiative. The Accords are designed to establish norms for the, quote, responsible exploration of the Moon and Mars. They cover key areas like safety zones, interoperability, registration of space objects, and perhaps most critically, the principles for resource extraction.
Okay, so what are the specific sticking points in the Accords when it comes to those resources? That sounds like a legal minefield.
It is. The Accords attempt to navigate the very complex legal landscape created by the 1967 Outer Space Treaty, which, prohibits any national appropriation of celestial bodies.
You can't own the moon.
You can't own the moon. But the Accords affirm that resource extraction like mining water ice is permissible, as long as it's conducted in a safe, transparent, and sustainable way, and that the resources themselves can be utilized. The goal is multilateral, consensus-driven exploration. And this massive coalition, now 60 nations strong, just reinforces the diplomatic weight of the program as the framework for operating in that cislunar domain.
And that sets the stage perfectly for the geopolitical tension here. Because we have the U.S. and its 60 partners actively building out the hardware and establishing their rulebook, But they are emphatically not alone in this endeavor. Governing requires agreement on resource rights, and China is making it very clear they have a very different roadmap for claiming and utilizing those essential lunar assets.
Absolutely. If the Artemis program represents one side of the ledger, this coalition-building consensus approach, then China's International Lunar Research Station, or ILRS program, represents the other. It's a highly centralized, aggressive roadmap focused entirely on resource security and operational permanence.
And the centerpiece of their immediate operational plan is the Chang'e mission, scheduled for mid-2026. This is where that strategic focus really comes to a head.
Chang'e is planned for a mid-2026 launch, probably around August, using their powerful Long March 5 rocket. And the target is the lunar South Pole, right near the illuminated rim of Shackleton Crater.
And this is an incredibly challenging mission.
Incredibly challenging and complex because they're sending a multi-component fleet, not just a single spacecraft.
A four-element mission. That suggests a degree of coordination and complexity that goes way beyond a simple landing and roving mission. What are the four elements and how are they designed to work together?
So the four elements are the orbiter, the lander, the rover, and this novel mini-hopping probe. The orbiter provides the global context and acts as a communications relay.
Standard stuff.
Right. The lander is the stationary observation platform, deploying instruments and making sure it lands precisely using a new deep space image navigation system. The rover performs the local surface analysis. But the key, the absolute key to the entire resource security mission is that fourth element, the mini-hopping probe.
Okay, let's focus on the hopper. Our sources describe this as a critical technological leap. It's designed to achieve a goal that traditional wheeled rovers are just physically incapable of managing.
That's exactly right. The primary target for resource extraction is water ice, and that ice is sequestered, it's stable, inside the permanently shadowed regions, the PSRs of craters near the South Pole.
These areas that never, ever see sunlight.
Never. Which means the temperatures are brutally cold and the crater floors are often treacherous, deep, and rugged.
Ugh.
A wheeled rover just can't operate in the pitch-black darkness for long, and it risks getting stuck forever.
But a hopper offers a completely different approach to exploring those areas.
A totally different approach. The mini-hopping probe uses highly controlled rocket propulsion to execute these short, ballistic, or sort of assisted flights.
Yeah.
This allows it to literally leapfrog over difficult terrain and, crucially, dip briefly into the PSRs, grab a sample, and then return to a sunlit, thermally stable location to analyze the data and recharge its batteries.
That's a high-risk, high-reward strategy.
Extremely.
And what specific instrument is the hopper carrying to actually analyze the ground?
Its primary payload is the Lunar Soil Water Molecule Analyzer, or LUWA. The mission goal is not just to confirm the existence of water. We've already done that with orbital data. The goal is to achieve the first in situ measurements.
Meaning on-site, right there in the dirt?
Right there. They need to analyze the form, the abundance, and the isotopic composition of the water, ice, and hydrogen directly from the regolith in these shadowed, ultra-cold regions. That level of granular data is absolutely essential for planning any future processing plants.
And the choice of Shackleton Crater as the landing site. That reinforces this entire focus on resource security, doesn't it? Why is this crater specifically the ultimate piece of lunar real estate right now?
Shackleton Crater offers this critical duality. Its illuminated rim provides excellent locations for continuous solar power generation and for communications relay, which you need for any permanent base.
Okay, so you have power.
But then, conversely, the crater's interior, especially the deepest parts of the floor, are in permanent shadow. And that provides the cold traps necessary for the stable, billions of years long preservation of water ice.
So you have proximity to power and proximity to water all in one spot.
Precisely. And the research team noted that laboratory simulations of lunar regolith support the hypothesis that the environmental conditions inside Shackleton are highly conducive to the stable preservation of that water ice. Securing this location essentially means securing the cornerstone resource for any sustained human presence.
Because water is everything.
Water can be split into breathable oxygen for life support and hydrogen-oxygen propellant for rockets. The nation that controls the water controls the logistics of the entire cislunar domain. This fundamentally pivots the global space race from science first to strategic resource security.
And that brings us right back to the geopolitical framework. Chang'e 7 isn't an isolated event. It's phase 4 of this massive strategic roadmap toward establishing the ILRS. How does that roadmap differ from the Artemis approach?
Well, the ILRS is China's direct response to the American-led Accords. And its approach is much more state-centric. It's focused on rapid build-out using their own internal technologies and a few bilateral partnerships, rather than a broad, consensus-driven coalition like Artemis.
So they're moving faster with fewer partners.
Right. Chang'e 7 is the scouting mission for resources and environment. The follow-on mission, Chang'e 8, which is planned for 2028, will specifically test key technologies for building habitats using lunar soil. That's known as In Situ Resource Utilization, or ISRU.
Building with what's already there.
Exactly. Building permanence using lunar concrete and resources, not materials you have to ship all the way from Earth at enormous cost.
This whole multi-phase program is explicitly aimed at getting a crewed lunar landing by the 2030s and building that permanent outpost. If they succeed, this sets up a fundamental conflict over jurisdiction and resource rights.
It creates an almost immediate jurisdictional conflict. The Artemis Accords, for example, establish safety zones around operational sites to prevent interference, a concept they've derived from international maritime law.
Okay.
But critics from the ILRS side view these safety zones as a subtle form of appropriation, a sort of land grab. So if China is first to confirm extractable resources in a key area like Shackleton Crater with Chang'e 7, and then the U.S. and the Artemis program follow shortly after, you have two competing legal frameworks being applied to the exact same physical territory and resources.
Wow.
The race is no longer about just reaching the moon. It's about whose governance model will dictate operations and resource distribution for decades to come.
That context makes the rollout of Artemis II and the imminent launch of Chang'e 7 feel less like exploration milestones and more like SMILs, opening salvos in a strategic competition for lunar logistics control. Okay, so before we shift from the moon to the crucial lessons learned in low Earth orbit this week, we actually want to hear from you. We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this escalating moon race and the rush for lunar water ice. And if you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future, right here on Tomorrow Unveiled. The tension we just discussed, the one about lunar resource control, is all about the future. But a really sobering event this week in low Earth orbit provided a stark reminder of the very immediate risks of the present. And that was the early return of the Crew 11 mission.
It was an unprecedented and critical event for the American-led space program. The mission, which was carrying a crew, including NASA astronauts Zena Cardman and Mike Finke, GXA's Kimia Yui, and the Roscosmos cosmonaut Oleg Platonov, it concluded roughly 4 weeks ahead of its original schedule.
And they splashed down safely.
Yes, splashed down safely off the coast of San Diego on January 15th, after 167 days in space.
And the reason for this early conclusion was a serious medical concern experienced by one of the 4 crew members.
That's correct. And it's important to note the distinction that NASA made, which was crucial for mission control. They characterized this as a medical evacuation, not an emergency deorbit.
And what's the difference there?
That distinction means that standard undocking and splashdown procedures were followed, which allowed for a controlled, predictable, and safe return. This wasn't a catastrophic failure of the spacecraft, but a calculated operational decision about a person's health.
Okay, but even as a controlled evacuation, the fact that an American-led crew mission has ended prematurely because of a crew member's medical issue, that raises immediate questions about our preparedness in orbit. I mean, they have a medical bay on the International Space Station, right? Why couldn't they manage this situation up there?
That answer highlights a major technology gap that our research team really emphasized. The diagnostic tools and, critically, the necessary specialized treatment medications aboard the ISS were just insufficient for proper diagnosis and care of this particular concern.
So they didn't have what they needed.
The decision was made that the astronaut required specialized terrestrial resources, specifically advanced imaging and detailed laboratory testing that simply do not exist in the confined volume of a space station.
We often visualize the ISS as this, fully equipped outpost, but this really shows its limits. It's a research laboratory, not a hospital.
That's exactly it. The entire architecture of the ISS's medical system is built on the premise that they are always just hours away from Earth and a rescue vehicle. They have excellent first aid, they have basic telemedicine capabilities, standardized trauma protocols, but they lack the depth for complex, non-acute diagnosis. They can stabilize a patient, but they can't diagnose a nuanced or complex internal condition that requires very specialized equipment.
It really shifts the emotional paradigm, doesn't it? Knowing that a crisis that's manageable in LAECO becomes a life-or-death timeline challenge the moment you move just a few days away at the moon.
That is the profound human lesson that's embedded in this evacuation. And while the mission directors stressed that the team responded decisively and safely, which is a huge testament to their training, this incident serves as a stark warning for the future.
Right.
In low Earth orbit, you can execute a controlled medical evacuation within hours. The Crew 11 astronaut received prompt care.
But once Artemis II reaches the moon, or we establish a base at the South Pole, that timescale shifts dramatically. A rescue mission would take days.
Days, not hours. And this event dramatically raises the required medical performance for any future deep space vehicles. We absolutely must bridge this medical capability gap before routine lunar operations begin, let alone a multi-year Mars mission.
So what does that look like? What do we need?
A lunar base or a Mars transit vehicle has to have exponentially better, almost fully autonomous medical diagnostic capabilities. We're talking about onboard mini labs that can run complex blood panels, non-invasive internal imaging devices, and AI systems that can assist the crew medic in making differential diagnoses without direct communication with specialists on Earth.
So the Crew 11 incident was a costly but necessary real-world stress test.
It was a stress test that defines the technology we absolutely have to build next.
That focus on bridging technology gaps and building robust, resilient infrastructure brings us perfectly to our third and final segment, the disruptive technological breakthroughs that were reported this week. We are looking at hardware that's built to last centuries, engineered to be reusable, and designed to think for itself.
Our research team distilled all the future-facing intelligence down to a sort of triad of breakthroughs that are fundamentally changing the physics and the economics of aerospace. We are moving from disposable structures and single-use engines to these long-life systems that redefine operational efficiency.
And nothing defines the new space economy more than the push for dramatic cost reduction. The data this week highlights the successful testing of the flight-worthy Zenith first-stage engine by a company called Space. We know the Nova rocket, which it powers, is aiming for 100% reusability. Why is this specific engine architecture the key to achieving that goal?
It all comes down to the physics of efficiency and durability. The Zenith engine is what's called a full-flow stage combustion, or FFSC engine. This is an incredibly sophisticated and, frankly, difficult architecture to perfect, but it offers just enormous efficiency gains.
Okay, let's take a minute to break that down. Full-flow staged combustion. We know what conventional engines do, but how does FFSC change the game?
Well, in traditional stage combustion engines, like the ones used historically, you divert a portion of your fuel and oxidizer just to power the turbopumps.
Okay.
And the exhaust from those small pre-burners is either partially wasted or just dumped overboard. But in FFSC, the breakthrough is that all of the propellants, the liquid oxygen and the fuel, are entirely processed through separate high-pressure pre-burners before they ever enter the main combustion chamber.
So there's no waste. You're maximizing the efficiency by using all the chemical energy that's available in the system.
Precisely. This design maximizes the engine's specific impulse, or ISEP, which is the measure of engine efficiency. By passing the full flow through the pre-burners, you get higher combustion pressures and higher thrust.
And that's also better for reusability.
Yes, and this is critical for reusability. The turbine drive gases that power the pumps are much cooler and cleaner because they're composed of pure oxygen and fuel gas, rather than partially burned exhaust products. This dramatically reduces the wear and tear on the complex turbo machinery.
So if this FFSC architecture is so much more efficient and cleaner, what were the engineering roadblocks? Why wasn't this adopted decades ago?
It's primarily been a materials and a manufacturing challenge. FFSC operates at extremely high pressures and temperatures. I mean, higher than almost any other chemical cycle. Building turbopumps and combustion chambers that can withstand those intense conditions for multiple cycles without suffering catastrophic structural failure requires cutting-edge metallurgy and precision additive manufacturing, which, were only recently perfected.
So the technology just wasn't there yet.
It wasn't. The Zenith engine's success shows that Space has solved those material science challenges, and they verified its performance on the vertical test stand this week up in Washington State.
And the Nova rocket, which is powered by this engine, is aiming to be the first medium-lift rocket to achieve 100% reusability for both its first and second stages. That is an aggressive goal that directly challenges the current market leaders.
It's the new economic mandate. Our dedicated research team corroborates that any launch system that is not aggressively moving toward 100% reusability for its core components will be economically obsolete by the end of this decade.
That's a strong statement.
It is. And reusability is what's fundamentally enabling these aggressive operational timelines. For example, the European Space Agency is already planning 65 missions in 2026 alone.
Wow, 65.
That's a massive 30% increase over their previous records. That kind of operational cadence is simply unachievable without guaranteed fast and 100% reliable reusability.
That economic shift is entirely predicated on hardware that can survive the orbital environment again and again. And this brings us to a truly radical breakthrough in material science. Self-healing composites. Our sources describe a composite material that's capable of repairing internal layers interlaminar delamination over 1,000 times. That number, 1,000 times, suggests a fundamental shift in design philosophy.
It absolutely redefines operational life. Delamination, which is where the internal composite layers separate under stress from micrometeoroid impacts or thermal cycling, that has historically been the primary failure mode limiting structural longevity.
And what's the normal lifespan?
Conventional spacecraft composites have a maximum design life of maybe 15 to 40 years. This new technology, which was primarily developed by researchers at North Carolina State University, suggests a structural lifespan that could extend to an estimated 125 to 500 years.
125 to 500 years. That completely redefines orbital infrastructure stability. But what's the hidden cost here? Does this technology add a massive amount of complexity? Or does it dramatically increase the initial weight of the spacecraft, which would kind of negate the reusability gains of the engine we just discussed?
That is exactly the right question to ask. The complexity is handled by embedding the healing mechanism itself, not by adding some massive external system. They use a two-pronged approach. First, a thermoplastic healing agent is 3D printed onto the fiber reinforcement layers in a very specific pattern.
And that pattern helps.
That pattern itself immediately increases the initial resistance to delamination by 200 to 400%. Second, they embed carbon-based heater layers within the composite skin.
Okay, so if a microcrack forms, how does the system actually heal itself autonomously?
It relies on a hardware-software symbiosis. The spacecraft's sensors, or its internal monitoring systems, detect the damage. An electrical current is then passed through the localized carbon-based heater layers.
Like a defroster in a car window.
It's basically like the trace wire in a defrosting element, yes. The heat that's generated melts the thermoplastic healing agent, causing it to flow into the microscopic fissure, and it effectively welds the separated layers back together, rebonding the material. And because the heating is so localized, minimal power is used, and the system can cycle hundreds of times because the healing agent remains integrated right inside the structure.
So the key takeaway here isn't just that the material lasts longer, but that the entire engineering philosophy shifts. We stop trying to prevent damage, which is almost impossible in the debris-filled environment of low Earth orbit, and instead we just focus on managing it.
The shift is from damage prevention to damage management. The goal is not pristine perfection, it's instant autonomous recovery. And this blueprint for long-life spacecraft skins is coupled with related research into what they're calling smart composites.
Smart composites!
Yeah, researchers at the University of Alabama, for instance, are creating composites with embedded fiber optic sensors that act as a central nervous system for the structure. These systems use real-time digital twin models, a perfect digital replica of the physical structure to monitor stress.
So it's self-aware.
If the sensor network detects a critical stress point, the software automatically triggers the electrical current to initiate the healing response before the fissure becomes a catastrophic crack. The structure becomes aware of its own health and capable of self-maintenance.
That concept of cognitive resilience and autonomy leads us perfectly to the third leg of this technological triad: quantum intelligence. A startup called Diffraction recently secured significant funding for its novel quantum camera technology. This seems like a fundamental leap in how we see the world from orbit.
It is a fundamental leap. It allows us to see farther, clearer, and faster with drastically smaller hardware. The core breakthrough is that this technology uses photon-counting sensors and advanced artificial intelligence to bypass the physical limitation known as the diffraction limit.
Okay, that sounds like something straight out of an advanced physics textbook. For those of us who aren't familiar with the physics, what exactly is the diffraction limit, and why is bypassing it such a massive deal for orbital observation?
Think of it this way. The diffraction limit is the physical boundary that traditionally dictates the maximum resolution a lens could achieve based on its size or its aperture. It's like trying to get a sharp photo with a pinhole camera. The physical aperture limits the clarity.
So to get a clearer image of something far away, you've always needed a physically larger mirror or lens.
Exactly. It's why we have to build enormous telescopes like Hubble or James Webb. The bigger the mirror, the more light you collect, and the better your theoretical resolution is.
And this new technology mathematically cheats that physical boundary. How does it do that?
By combining advanced quantum sensing with AI synthesis, the system doesn't rely on brute force light collection. It uses these highly sensitive photon counting sensors and then applies complex algorithms and machine learning, the AI part, to reconstruct the image data, overcoming the limitations that are normally imposed by the size of the lens.
And what are the performance metrics on this?
Diffraction's quantum imaging system claims up to 20 times higher resolution and 1,000 times faster processing compared to conventional systems using standard electronic sensors.
Those numbers are just astonishing. So what does this actually enable in a practical, operational sense up in orbit?
Well, this completely revolutionizes what's called space domain awareness, or SDA. Historically, high-precision surveillance and tracking capabilities were exclusive to major superpowers who could afford to launch massive multi-billion-dollar platforms.
Right.
Now, smaller, low-cost satellites, even CubeSats equipped with this quantum camera, can achieve that same level of high-precision surveillance.
That democratization of orbital clarity is a major geopolitical shift.
It absolutely is. The funding they secured, which includes a specific contract for the U.S. Space Force's Apollo Accelerator program, is aimed at tracking minute orbital debris and identifying the stealthy maneuvers of other spacecraft in real time. But the broader impact is that the barrier to entry for high-fidelity space intelligence is dramatically lowered.
So anyone can have spy satellite quality images.
If commercial entities, universities, or smaller nations can launch small, low-cost platforms that provide superpower-level clarity, the orbital playing field is completely leveled. The space above us just became a lot more transparent, and the implications for everything from defense to commercial Earth observation are enormous.
This has been an incredibly packed week of developments in space, a true pivot point in history. Let's just quickly synthesize the core themes we've seen confirmed by our dedicated research team.
We started with the grand scale and the immediate future. You have the Artemis cluster rollout, which is validating the entire human-lunar logistics chain, and then the diplomatic victory of the 60th signing of the Artemis Accords, establishing the American-led governance framework for deep space.
We then immediately contrasted that with the aggressive, resource-focused roadmap of China's Chang'e mission, which is deploying its unique hopping probe to secure resource dominance at Shackleton Crater. This confirms that the race for the moon is now explicitly a strategic competition for control of lunar water.
And then we had the immediate, stark lesson from low Earth orbit, the Crew 11 medical evacuation. That incident underscored the vital, urgent need for autonomous, deep space medical diagnostic and treatment capability, especially as we plan for lunar bases where rescue is not guaranteed within hours.
And finally, we looked at the technological leaps that promise to secure that long-term future. The Zenith FFSC engine and the economic mandate of 100% reusability, the self-healing composites capable of centuries-long structural resilience through damage management, and the quantum cameras bypassing physical limits to revolutionize orbital intelligence.
The overall core takeaway, derived from the analysis provided by our research team, is that the space economy's true value now lies in the connective tissue, the resilient, self-maintaining infrastructure, the autonomous systems, and the logistics networks that are being built right now. It is the transition from high-cost, high-risk discovery to profitable, permanent deployment.
And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
And we love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the future of self-healing spacecraft materials. Do you think 500-year spacecraft are truly feasible? Or will micrometeoroids always win the day? And here's a final thought for you to reflect upon. Since the competition between the Artemis program and the ILRS is focused entirely on securing water and resources at the moon's south pole, and this technology for self-healing materials promises to extend the life of lunar habitats for potentially hundreds of years, the ultimate question isn't just who gets there first to extract the ice. It is whose framework, the Artemis Accords or the ILRS roadmap, will govern permanent infrastructure and resource rights over the next 5 centuries. If our bases on the moon might outlast the terrestrial nations that built them, what sophisticated long-view legal and ethical framework do we need to implement today to truly govern the future of humanity off-world?
A profound question to end on. Join us next time for another in-depth analysis of the future here on Tomorrow Unveiled.